Cool. All right, so let's talk. We're going to start this lab today, and we'll finish it up on Monday.
Yay!
Okay? So this whole concept of electric fields and forces. So you can make somewhat of an analogy that an electric field is somewhat like a gravitational field. So let's say, for example, you wake up in the morning and you go, wow, is gravity still a thing? Is gravity still working? Are we in a gravitational field? So what's one thing that you could do, very simply, to check that gravity is still working? Jump. What would happen?
You come back down.
You come back down, okay? Or just drop something, right? Because if I drop something and there is no gravity, what would it do?
Just stay there.
It would just stay there, okay? Louis?
Yeah.
Fish?
Yeah.
I'm sorry.
I was so confused what you were saying.
Okay?
You said my name.
Because if there is no gravitational field, it got switched off overnight, okay? We didn't pay the gravity bill, whatever. And you let go of something, it's just going to stay there because there's no force to cause that acceleration. Now, we do the same thing with electric fields. So if I've got this balloon over here, and I want to determine if there's an electric field around it, okay? I need to somehow put something in there that can test that. So right now, if I put my hand up here, and I'll use my, get that squirrel.
Oh yeah, sorry.
So if I put my hand up here, nothing happens. So my hand is what we call the test charge. So a test charge is what you put into an electric field to see the impact that it has. So, but if I take this balloon and I charge the balloon, okay, then when I put my hand here, then I see that something's going to happen. So typically when you look at this situation where you're trying to find the effect of the field, gravity is a one-trick pony. You know if that gravitational field is there, it's always going to fall towards the center. In this situation, imagine that this is anchored. So typically what's going to happen is that you anchor the charge that's creating the field. Now, that's negatively charged. When you look at fields, you always use a positive test charge. That's just how we define it. You always define it in terms of a positive test charge. So if this is my field that's generating this, and my hand is positively charged, so that's a negative field, okay? So if I put my hand here, which is positively charged, what's my hand going to feel?
Attraction.
It's going to feel an attraction, okay? Now, if my hand is negatively charged, what's going to happen? It's going to be repulsed. Or if this is my positive test charge and the balloon was positively charged, it would feel a repulsion. So how you define an electric field is the impact that it has on a positive test charge. Now, here's the story. Let's say, and this is a similar analogy, okay, so give that a spin. So, I have Hank the bowling ball, and I got a ball of twine. If I drop them both at the same time, what do you know about their accelerations? They're the same, okay? They're both going to accelerate at the same rate, even though they have different masses. So the acceleration is going to be the same, independent of the mass. What is going to determine the acceleration? Not this mass, but what is going to determine the acceleration?
The distance.
Mass of the Earth and how far you are from the Earth, right? Okay? So this doesn't matter. I'm going to have the same acceleration. So the same thing is going to be true of a test charge. The charge that's on the test charge doesn't matter. You just have to know that it's a positive value. Okay? And then you look at that influence. Morella.
Which one's the test charge again?
Hold on.
I
I haven't designed anything yet.
Oh.
So what's going to
I
happen?
thought you said what it was.
So that would be the source, that in this analogy, the Earth and when I check for an acceleration, the Earth is at the center, and I check the gravitational attraction towards the Earth. That's generating a field. So that balloon is like the Earth, okay? So when I put a positive test charge near it, if that test charge gets attracted towards the balloon, I know that the balloon is negatively charged.
Okay.
If my positive test charge gets repulsed by it, then I know it has a positive charge. But the value of the charge, of the test charge, doesn't matter. Just like the mass of what I drop doesn't matter. Fish.
Could that be neutral still, or does it have to have a positive or negative? Like
Yeah,
it's
if it's neutral, then it doesn't have, there's no field around it, and nothing's going to happen.
okay.
So what's at the source has to either be a positive or negative charge. Okay? Now, so here's the deal. So if you look at how you calculate a gravitational attraction between 2 points, there's 2 criteria that have to be met. You have to know the masses, and you have to know how far apart they are. Now, but if you simplify this and you say, okay, well, we know that Fg equals mg. So if I wanted to calculate the weight of a 1 kilogram mass, I could go, oh, that's 1 kilogram times 9.8 meters per second squared. That also equals big G, that's mass 1, mass of the Earth over distance squared. Remember this, okay? These 2 values are the same. So that cancels out. So my gravitational acceleration is only dependent upon the mass of the Earth, how far away I am from the Earth, and some constant, okay? So what determines the acceleration is not the mass of what's falling. It's the mass of the center. Same thing is going to be true of an electric field. So let's talk about the difference between these. So here I have F equals K, Q1, Q2 over D squared. So if I wanted to calculate the actual force between the balloon and my positive test charge, I would have to know 2 things. I would have to know the charge on the balloon, and I would have to know the value of the charge on that positive test charge. Then I'd have to know how far apart they are. So if I know these things to actually calculate the actual value of the force, I'd have to know the source, I'd have to know the other value of that test charge, and I'd have to know how far apart they are. Now, but a lot of times when we talk about electric fields, we don't care about the value of the test charge. The only thing we use the test charge for is basically to say, okay, hey, which direction is that going to go and what's the value of that? So if you look on this purple sheet, okay, you have 2 different ways to calculate electric fields. So the first one, and let's actually back up and how your sheet lists this equation. 1 over 4 pi, not what I did.
Oh.
No idea how that happened. 1 over 4 pi epsilon naught, we'll talk about epsilon naught, K, or then Q1, Q2 over D squared. So this is what's on your actual sheet. This epsilon naught is what's known as the permittivity constant. Don't worry about it, it's just a number for now. So this, when you simplify it, just becomes that value of K, which is 9 times 10 to the 9th. So your actual sheet doesn't list it as K, Q1, Q2 over D squared. They list it as 1 over 4 pi epsilon naught. Once we get into electromagnetic radiation, we'll talk more about that epsilon naught value. It's just a number. But if you take 1 over 4 pi times that permittivity constant, you're going to get the K value, which is 9.0 times 10 to the 9th. So that's, I don't know why they'd make it this way. Everybody listed as K, Q1, Q2. They want to get Q'd and listed as 1 over 4 pi epsilon naught. Why, I don't know. I just wish they would put it as K. Now, here's the next equation. Next one down, okay, over here on this purple sheet. You have E equals F over Q. This is normally expressed as FEC, okay? So if you solve for this, this is what you get. So what this tells you is that this is the value of the electric field. Now, here's the story. If you look at the units, your electric field, if you start with the electric field equation, that force is going to be in newtons, that Q is going to be in coulombs. So any electric field strength is measured in newtons per coulomb. So it's somewhat analogous to a gravitational field. So a gravitational field, if you think about it, you could express as newtons per kilogram. Okay? Well, here I've got Hank, right? Hank has a very, very large mass relative to the ball of twine. So the gravitational field, okay, instead of an electric field, you talk about a gravitational field. This has this has less force per kilogram. This has more force, but there's also more kilograms, okay? The value of the gravitational field has the same effect. So when you look at an electric field, the units are newtons per coulomb. So the strength of the electric field is determined by how much force that exerts per coulomb of charge. So if you have more force, that means that electric field is going to be stronger. So if you simplify this and just do a little bit of rearranging, then if you look at what happens with the units. So any electric field is newtons per coulomb. If you multiply that by the charge in coulombs, the coulombs cancel out, you get units of force, boom, we're done. Okay? So if you simplify this, so if you know, for example, here's a charge and it's emanating some electric field. So if you know what the strength of that electric field is at that point, and you know the charge that's out there, then that's going to tell you how much force is going to be exerted at that point. Now, when you look at this value of Q, okay, this is going to be important in terms of this lab. That Q is not the value of the test charge. This Q is what's creating the field. Just like if you go back to the gravity analogy, the mass of the earth is what determines the acceleration, because that's like at the center. So this Q is the point source. That's what's creating that electric field. So, got that idea. So where this comes from is if you look at, I'm going to combine a couple of things. So if I wanted to look at this in terms of taking the value of that force, and I want to figure out how much force there is per unit of charge. So if I do this, then because I'm going to have two different charges, what's creating the field and what's experiencing the field. So I'm going to have two different values. So if I want to look at this in terms of how much force there is per unit of charge, then if I do that, that Q is going to cancel out. In the similar idea that if I have a bowling ball and the earth, and I want to calculate the acceleration of the bowling ball, mass of the bowling ball doesn't matter. So the same thing is going to happen here. The charge that's out there doesn't matter. What's going to matter is what's creating the force. Louis.
Should that be E instead of F?
No, it's because the F itself, that's how you're going to calculate the force. Okay?
Okay.
So that's KQ1, Q2 over D squared. So this is just going to be the force. But what I'm doing is if I want to find the force per unit of charge, I'm going to divide it by the charge that's out there in the field, not what's creating it. So all I want you to see out of this is that what's going to determine the value of this field, okay? Because if you look at this, if you divide both sides by Q1, what's going to happen is that what I want you to see out of this is that what's going to determine the strength of this field is what's at the source, not the value of the test charge. Just like what determines the gravitational field of the earth is based solely upon the mass of the earth, not what's falling.
Yeah.
So when you look at these equations of E equals F over Q, you don't need the value of the test charge to figure out the value of the electric field. Just like I don't need the mass of what's dropping to figure out the acceleration on the earth. Okay, because that cancels out of the equation.
Okay.
That's all I want you to get out of this. Okay. Now, so the other way that you can express electric fields is this next one down here. So you have E equals K, which is that 1 over 4 pi epsilon naught, Q over R squared. Now, that's what I did up here. So this here, this next equation down, let me rewrite that because that was just horrible. KQ over R squared. Okay?
Is that just Q or Q1?
No, that's the Q, which is going to be at the source that's creating it. So when I took this force and divided both sides by charge, okay? So we just said up here that E equal to F over Q. So when I divided it by Q, now I'm talking about the value of the electric field, which is KQ over R squared. So you end up with the same thing. It's just two ways to get there.
Okay.
So when you look at this, how you can calculate an electric field, there's two ways, okay? You can take F over Q, which gets you newtons per coulomb, or you can do K times Q over R squared. Now, here's where the magic happens. And it just depends on what you're given in the equation. So if you look at the units, that K is newtons meters squared over coulombs squared. And then that Q is going to be in coulombs. And then you're dividing that by meters squared. So then you lose one of the coulombs, you lose the meters squared, you get newtons per coulomb, which is the exact same units you have if you take force and divide it by Q. So no matter how you do it, you end up with the same idea that is newtons per coulomb. Okay, so again, here's the main thing if you combine these two ideas. Notice that the strength of your electric field is divided by R squared. So if I double the distance from the source, what's going to happen to the value of the electric field?
It's gonna
Decrease by a factor of 4. Okay? So if you're, and this is one of the things you can do in this lab, is that you're going to determine what happens to the strength of an electric field as you go further and further and further away. And what you should see is that it produces this nice inverse square relationship that as that radius gets bigger and bigger and bigger and bigger, the strength of that electric field becomes smaller, which is the same idea of a gravitational field, okay? Because a gravitational field is big G mass over R squared. Oh, I double the distance away from the Earth, oh, G becomes 1/4 as much. I double the distance from the point source of an electric field, the electric field strength becomes 1/4 as much, okay? Same mathematical idea. But what's important is either the mass of the Earth, the charge at the point source. The test charge or the mass that I drop doesn't matter, not part of the story. Okay, now, when you look down on this next one, you have V, well actually you're going to skip one. You have V equals, and again they have 1 over 4 pi epsilon naught, which is just K, Q over R. Now, let's talk about this. So, I'm going to get to the units for voltage. That V stands for voltage. That is not velocity, it's not volume, it's voltage. Okay? So, if you look at what happens with units. So here's K, which is newtons meters squared over coulomb squared, times coulombs. But now we're only going to divide by meters. Okay? We're not going to divide by meters squared, we're going to divide by meters. So, I'm going to cancel out one of the coulombs. I'm going to cancel out one of the meters. Now, what do I get when I multiply newtons times meters?
joules.
Oh, I get joules per coulomb, which is the amount of energy. So for those of you just were in my AP chemistry class, we just talked about voltage. And
Yeah, that's not.
joules per coulomb is measure of energy per unit of charge. So there's a good book. It's called There Are No Electrons. Okay? So it's an odd title, but it's a good read. And so it explains electrons in terms of little particles called greenies. So we're going to be talking about three big ideas. And so I'm going to kind of lay the groundwork for what joules and how all this plays out in volts. So if you imagine a dam, okay?
A what?
A dam. It's going to hold water. A dam, just a dam. Okay? And it's going to hold water. So if you imagine this in terms of the height of the water being the amount of potential energy that you have. So you can think of this as like energy per drop of water. Okay? So the height of that dam determines the energy per drop of water. That height is equivalent to voltage. Okay? So your voltage is how much energy there is either per drop of water, if you want to go with the dam analogy, or it's energy per unit of charge if you're going with the electricity analogy. Okay? The higher the water is, the more energy there is per drop, or the more voltage there is, the more energy there is per coulomb. Okay? So that's your voltage. Now, that has the potential to move downhill. Okay? So that voltage is going, you're going to let that water go downhill. And you have two ways that you can do that. One, you can have a really small straw. The other one, you can have this big massive pipe. Okay? Which one's going to allow more water to flow through?
Big massive pipe.
Big massive pipe. So how much water flows through there is current. And that's shown by the letter I. Okay? Yeah. And that is also measured in amps, which is coulombs per second. So amps is how much charge flows through per unit of time. So if you have this big massive pipe, that's going to allow that water to flow through very quickly. That's going to be a very high amp system. If you have a little straw, it's not going to be as much. Okay? But they have the same potential. They're starting with the same potential energy. So the voltage is the same, but the current is going to be different based upon the size of the straw.
It's how much it can flow from one thing to another.
Exactly.
Okay.
So the higher the amperage is, so like for example, if you've ever looked at the breakers in your house,
Yeah.
breakers on your house might be like 15 amp breakers.
Yeah.
So if that exceeds that 15, it throws the breaker.
How would it exceed that 15? How does it like?
Basically, we'll get into it. Typically, what happens is that when you're having too many things going at the same time, like the vacuum cleaner, an iron, a heater. Okay, you have everything on the same circuit, and it's going to draw so much power that it overloads that 15 amps, and then it throws it.
So why is that bad?
Well, you just, because that system is, all your houses are designed in parallel, which is a whole other discussion, which we'll get into, okay? But your current, all your utility, your ironing board, your coffee maker, or whatever, are designed to have a maximum of 15 amps. So if you have more than that flowing, that's also going to be flowing into your appliances, and that's going to damage your appliances. So basically, it's a self-check thing to protect your appliances from exceeding that 15 amp limit. Okay.
Is there an equation for amps? Would just be like.
Oh, yeah, there's a whole bunch of equations for amps. Don't worry about it for
This
now.
is a really big, a lot of equations.
Oh, there are a lot of equations.
Either mine,
Okay, there's a lot of equations. Okay, now, the last one is resistance. Resistance is basically how easily the water flows through the current. So, if there's just ohms, okay? So those are going to be the big three. Current, which is in amps. Voltage, which is what we're going to need for today's lab. Don't worry about current, don't worry about resistance. The only thing you need to know for today is voltage. And it's how much energy there is per unit of charge. It's joules per coulomb. Okay. So, if you look at this one for voltage, which we said was KQ over R, what that reduces down to is joules per coulomb. That's how much energy there is per unit of charge. Now, you also have, and this is a weird way they do this, they have E equals, down here on the next one down, they have delta V over delta R, which is just completely jacked up. So mainly because most of the time it's just voltage divided by distance, and I don't know why they put it as delta V over R, it's voltage over distance. So if you look at this in terms of this, so again, voltage, right? And this is the strength of your electric field, okay? So you have E equals delta V over R. So typically your voltage is going to stay the same. So as you divide by a bigger and bigger distance, what's going to happen to the strength of the electric field? It's going to become smaller, okay? Because you're further and further and further away from that value. Okay, got that basic idea?
Yes, sir.
Okay. Now, what you're going to do is, come on, here we go. So what you need to do, and this is going to be done on your Chromebooks. You want to search for FET, and then
Fat fuel hockey, right?
no,
Oh, yes.
no, hold on, I've got it on the
Electric
lab.
Electromagnetic spectrum?
No, charges and fields. That's what you need. I've got it on your. There it is. Charges and fields.
Can we do this in groups, or does it have to be alone?
No, you can.
Okay,
Okay.
cool. I don't have a computer.
So when you do this, this is what you're going to pull up. Just hit play. Now, so there's this thing has some very, very cool features. So what you want to do is you want to turn on a whole bunch of things. So, let me turn on the lights so you can see this.
Oh, no way I hit clear.
Okay. So what you've got is a series of grids, and this looks a little wonky on my television. But what you can do is basically, the first thing I want you to do is try and figure out what's going to happen. So you're going to drag like a positive charge, and you're going to put it right there. So what this is showing is, it's cool because you have a positive charge. So notice that those arrows are pointing away from that positive charge. Why? Because if you put a positive test charge there, what would happen? It would repulse, okay? So, and the intensity of the light shows the intensity of the electric field. So as you get further and further and further and further away, notice that, number one, it still points away from that, but that strength of that electric field becomes smaller. Now, one of the things you can do is come over here and you can drag this sensor. And what it does is that shows the voltage at a particular point. So notice when you get closer, that voltage goes really, really high. As you move that thing away, the voltage becomes smaller. So it's kind of like the somewhat analogy of like a mountaintop. So when you're really close to the mountain top, you have a lot of like gravitational potential. And as you go further away from that mountaintop, that potential becomes less and less and less and less and less. And that's what's happening here. So this is a tough thing, but it's handy. Imagine that you could flip this over. Okay, so instead of looking flat, imagine that this is like a mountain. And at the top of that mountain sits a positive charge. Okay? And when you're moving further away from that, imagine that mountain is becoming more and more shallow. So you have less and less and less of a certain amount of energy. Instead of energy per unit of mass, which is you have a bowling ball, whatever that is, this is going to be energy per unit of charge. So that's one thing that you can do. Now, if you hit the little pencil icon, so what that does is that draws a line of equal potential all the way around that point. So what I want you to see here is that notice that these field lines are at right angles to the lines of equal potential. Okay? So as this is going out, your field lines are going like this. They're at right angles to them. You can also, and you're going to need this, it's equipped with like a little tape measure. So you're going to also have to measure distances. So you anchor your tape measure wherever you want it, and then you can drag that tape measure out, and it's going to give you a distance. Or if you're anchored, then you can move the whole thing and see where you end up. Okay? So then down here, this yellow button down here, the sensor, if you drag that, what that tells you here is it's the value of the electric field, because notice this is volts per meter. So, and it tells you the angle. So in this program, 0 degrees is here, counterclockwise, all the angles are going to be measured around like this. So if you move that sensor around, okay, then you're down in here to negative degrees, positive degrees, and notice that as you get closer, if you bring that sensor closer, notice that that line gets bigger because of the fact that as you get closer, there's more volts per meter. That's why that line becomes bigger. So there's a whole bunch of different things you can measure. You can measure the voltage. You can measure volts per meter. You can indicate the value of the charge. You can put negative charges. You can put positive charges. There's a whole bunch of different things you can measure. And each one of these grids represents a half meter, because when you begin to do some measuring, that's a cool thing to know. Okay, so stop that camera. Let me hand out.
There we go.
All right, so on part one, the only thing I want you to do with this first part is just get a feel for the program, okay? So you're going to take a positive, and all of these are 1 nanocoulombs. This is going to be important later on when you start doing the charges. So each one of these, positive or negative, is 1 nanocoulomb, okay? Not 10, not 20, 1. So the first thing I want you to do is that you're going to say, hey, how does that voltage number change? Does it increase, decrease, stay the same? How does the color in the circle, or how does the color in the circle with, that should be changed with crossovers. How
What's
does
a
the color in the
crosshair?
circle with crossovers change?
Like-
Oh, it does make sense. I put change on the end. Okay. Basically, you're going to look at how that intensity plays out. Then you're going to swap out a positive charge, and then you're going to put a negative charge. So tell me what's different. Tell me what's the same. Now, then you're going to go back to putting a positive charge, middle set of coordinates, move the voltage meter so that its crosshairs are 0.5 meters away from the positive charge. Then what you're going to do is you're going to click that pencil icon, and you're going to draw a series of concentric circles. So what you're going to do is, this is the one graph that you have to draw. So you're going to have the radius from 0.5 to 1 to 1.5 to 2, electrical potential, which is that voltage. Then you're going to draw that graph. What do you notice about the direction of the field in terms of the positive charge and the equal potential curves? Address that question. So basically, if you can get through part one today, that's as far as we need to get. Okay? So just get through part one. All right, you're on your own. And I'll give you a sheet of graph here.
You said the voltage increases the closer it gets to the growth.
Or the charge, the positive charge. And the color fades as it gets farther from the charge.
Yeah, I'll take a 10-minute nap.
What'd you say for the color?
It fades. Okay, replace the positive. Here, let's get this out of the way.
You just went bonkers. I don't know, but then
Can you use the
you
restroom?
one of them and it screws up the first one, bro.
What?
That's how far I got.
Okay,
That's like where I was at.
negative point charge.
And I put a couple more blue ones and I made it just go
I'm
around.
probably not good because I didn't finish two problems. I didn't finish like half of the problem.
The voltage.
I think that's why I missed.
Half of the A problem or half of the problems?
Half of a problem.
I probably got like a
The voltage is a negative value, but still increases.
Or was it electrical? I didn't finish the second.
Yeah, I got like a 12. B plus 88.99.
Different one, the voltage.
A negative value, right? But it still increases, right? As you
The
get
magnitude's the same, it's just the.
yeah, yeah. The sign, the voltage is a negative value.
Hey, you dropped
Sign.
it.
Opposite sign.
Thank you.
Throw it at him. As hard as possible.
Same is magnitude increases. As you get closer, or as the probe gets closer.
Okay, okay.
Jenna,
What's up?
how'd you feel
Put
about
the trace on.
No. I didn't read the book.
You should check your Skyward.
Put the
I don't
field
want
on.
to check
That's
Skyward.
all the field.
What'd you get, dude? You just put it in our quizzes.
Put your
I don't want to yet.
Fry.
You should take a checky.
Yeah.
I told him I didn't read it.
Put the field on.
Okay.
I didn't read it.
Replace the negative charge with the positive charge. Place it so that it is in the middle of a set of coordinates.
Oh, absolutely.
First, explore the placement of one.
What's that even mean?
Okay. What's your question? Ask.
Move that.
Probe display.
The VPD. So that crosshairs are 0.5 meters away from the positive charge. I think we have to use that.
Well, one of these is 1 meter, so it's just like one of the squares.
This is it.
0.5 meters is 50 centimeters. A circle should appear. Wait. Oh, click the pencil. Pencil. Repeat this process for one. So, it's just another one of these. It's for this, for 1 meter, 1.5, and then